Hello. Today we will start with a new topic in our introductory guidance to quantum mechanics series. It's about the time-independent Schrodinger equation, which is lesson 8. From this title, we can guess that we are trying to deal with some new terminology, which is Schrodinger equation, but it is in time independent. That means we are not taking the time dependent part of this equation in this class. So from the start of this course, we have discussed several topics, and we have noted that we are going to talk about this important topic later on. So by starting this topic, Schrodinger equation, it is one of the most famous and short equations that is introduced frequently in quantum mechanics. So to tell about the importance and the origin and what is exactly this equation is about, we shall first start from the fact that in quantum mechanics we describe systems using wave function. So the particles or electrons has dual nature. That's mean particle and wave nature. Then when we treat a system as wave, the wave function represent the displacement or the amplitude of that wave produced or generated from that particle or electron. So if we treat the system as a particle, then the wave function is used to give us probability of finding the particle at some moment of time and space, which is described in absolute psi square, which is psi is the Latin word that we are reading the wave function. So it's the absolute value of the square of wave function. So this is the wave function, square root of the wave function. And by this value, we usually describe the particle, such as electron in quantum mechanics. So, absolute of the square of the wave function, in order to describe any particle in quantum mechanics, we shall be able first to determine the wave function numerically, as well as it is a solution for Schrodinger equation, which is differential equation in its nature. So in Schrodinger equation, as we have mentioned, it gonna deals with the wave nature of the particle. So it's not other nature or I mean particle nature. Particle, it's described in terms of waves. So in the same way, with the well-known Newton second law motion equation, which is the summation of the forces, which forces equal mass multiplied by the acceleration. So the Schrodinger equation was invented in the same, way, that is, it's experimentally confirmed. So there is no way to derive the Schrodinger equation mathematically. So we are starting from some point and we are trying to deal and we're trying to find solution for this equation. So what does Schrodinger equation forms that usually show or have? So in order to determine which forms the equation takes, we shall use the conservation equation. So in this class, we will also assume that the wave function doesn't depend on time and only depends on spatial position of the system. So we are treating the wave function in its x value. So it may has other dependent variables such as time or something else. But in this class, we are up to discuss only one dependent factor, which is the position. That means the particle moving in the x direction. But later on in the coming lectures, we're gonna treating the other dependent variables. So imagine in this point that the electron is moving with the positive direction without any external forcing affecting on it. So it's moving freely, which means that it has constant energy and momentum. So from de Broglie equation, the momentum equal h, which is Planck constant, divided by the lambda, which is the wavelength of that electron particle. So, as in our previous assumption, we are assuming it's freely constant momentum and constant energy moving with the x direction. So we are expecting at the same case. So if this is constant and this is as well as it's Planck constant, it's constant itself. So we will have lambda also constant wavelength as well. So in our expectation now, that the wave function under previous assumption maybe satisfies with the classical equation of the wave function. So what is the classical equation of the wave function? This is, we are starting from the classical equation of the wave function. So it's psi x of t, x and t dependent function. This is time and this is the position. So a sine k of x minus omega t plus b cosine k of x minus omega t. So in our assumption that we are assuming it's independent of time, so time equals 0. So this is how the equation would look like. So this is the first, equation number 1. So it's start with a constant a sine and b cosine. So this is constant value a and b, and this is cosine and sine functions. So this is star 1 equation. So it's a free particle wave function, i.e. no forces applied and Schrodinger solution applicable. So this could be one of the solution for Schrodinger equation. Only function of the position change over x-axis. So it's x dependent function. It's independent of other function like time. So k also it's constant, and it's equal to pi divided by lambda, and lambda from classical physics equal h divided by p. This is Planck constant. So k equal p divided by h divided by 2 pi, and this is equal p divided by h prime, which is we have discussed before, and it's also constant in itself, which is equal 1.06 10 to minus, this is I think minus 34 joule divided by second. So this is minus, not positive. So approaching into energy conservation as the presented particle must, the particle must has its own mass m, and it's moving with velocity v. So the total energy of this system, the moving particle, it has to have kinetic energy and potential energy in the same time. So the kinetic energy, non-relativistic kinetic energy, it's 1 divided by 2, which is half mass velocity square plus the internal energy. And we may recalling some values of the momentum, which is mass multiplied by the velocity, and velocity equal momentum divided by mass. So substituting these values, we may get, instead of the velocity equation, that energy, which is the conservation equation, energy of that system particle equal 1 divided by 2 momentum square divided by mass of the electron plus the potential energy. And this is again also recalling that momentum equal k multiplied by h prime. So finally, the final form of the independent Schrodinger equation must satisfy this form, which is k square h prime square divided by 2m plus u. So we are here just simply substituting this value to here, and finally we get this final equation form, and we are noted this equation as equation number 2. So equation number 1, that this equation, so this is actually the solution for Schrodinger equation, while this is the form where is the Schrodinger equation must satisfy or looks like. and this equation 2 is generated and checked to be found from the conservation equation. So as we are dealing with the time independent Schrodinger equation, we usually eager to looking for differential equation that's look like 2 and it has a solution satisfied with one equation. So this is the form 2 is the form, this is the form 2 equation, this is the form where the Schrodinger equation looks like, and this is the form of the solution of that Schrodinger equation, time independent Schrodinger equation. So from the equation number 1, we simply take the second derivative of that equation, and it will generated and resulted to be this value of Schrodinger equation. This value itself, it's also the same with the first equation value. So this is the wave function value generated also in the second derivative of the first equation. So it is differential equation as we are close to determine the 1D, one dimension time independent equation. So it's differential equation. So we are getting closer now to solve and find the solving by finding the time independent Schrodinger equation. Now we shall make equation 2. Equation 2 looks like equation 3 because both of them has common value, which is k squared. So we are able to multiply equation number 3, so multiply by minus h prime divided by 2m to make both of those equations looks similar, to treat them in some different manner. So this is equation number 3 as it here. This is equation number 3 here. Multiply by minus h prime divided by 2m. So we're gonna get this equation. So again, recalling from equation number 2, this value it's also in equation number 2. So again, we're gonna multiply equation number 2 by wave function. So it will resulted with this distributed equation. It's simply just rearrangement and substitution, and finally we're gonna get the first dimension time independent Schrodinger equation, and it's usually not a derivation of the Schrodinger equation, rather than its determination to check its validity through experimental test. And this is simply what is the time independent Schrodinger equation, and we're gonna continue in the coming lectures by other derivation and formation of the Schrodinger equation. Thank you.